Hello. Today I will be presenting to you pharmacokinetics and the math behind its application. What is pharmacokinetics? Pharmacokinetics is the study of the process that consumable substances in the body undergo, starting from ingestion to excretion. Along with pharmacokinetics, we also have pharmacodynamics. Pharmacodynamics is the study of the effects of a drug inside the body and how it interacts with bodily fluids in the site of the action. Basically, the difference between pharmacokinetics and pharmacodynamics is that pharmacokinetics is the study of what the body does to the drug, and pharmacodynamics is the study of what the drug does to the body. We'll mostly be getting into pharmacokinetics and the math behind it, but I wanted to go ahead and explain what pharmacodynamics was also, since it's also similarly named, and so it does not get confused. For pharmacokinetics, we have the 5 steps of Ladme, which is liberation, absorption, distribution, metabolism, and excretion. Liberation. This is the release of the drug substance. This is also the same as when you take a gel capsule and the outer layer breaks down, releasing the contents. Next is absorption. This is when the drug is absorbed into the body through the bloodstream. Next, distribution. This is the dispersal of the drug throughout the body. In the case of a pain-relieving drug, this is the point when the pain relief begins to spread throughout the body. Metabolism. This is when the body processes and breaks down the drug. This is also the point when the pain relief begins to slowly fade away. And lastly, excretion. This is when the drug exits the body. This is also the point when the pain relief would completely subside. Now that you know pharmacokinetics and the 5 steps of Ladme, we can get into the math behind it. For doctors to properly prescribe a correct dosage of a drug for a patient, we must understand its concentration over time, and to do this, a differential equation will be used. Keep in mind, a differential equation is an equation that relates functions and their derivatives, with the functions usually representing a physical quantity and the derivatives representing their rate of change. Thus, when using a differential equation for pharmacokinetics, it will describe the relationship between physical quantities of a prescribed drug and the rate at which they change. All this allows a proper prescription to be made to prevent under or overdosing. Differential calculus involves finding the rate at which a variable quantity is changing. Take, for example, dissolving a drug in a cup of water, the rate of which is determined by the rate the drug is diffusing away from the surface of the solid drug. This can be expressed by the Whitney equation. The Whitney equation has its own set of variables. Pharmacokinetics uses the concentration of a drug as the variable quantity and the time as the independent variable. This is just one example, where we're going in depth with a different equation and its own variables. To create the differential equation that will describe the physical quantities of a drug and their rate of change, we will consider these variables first, with D representing drug dosage in milligrams, C the concentration of the drug at any time, and T time in hours since consumption of drug. Along with the first variables, we will also consider these variables: Ka, the absorption constant of a drug; Ke, the elimination constant of a drug; V, the volume of a drug in the body; B, bioavailability. And keep in mind, bioavailability is the amount of drug already absorbed divided by the total amount of drug that is available. To start with, the equation for absorption. Using the absorption constant, the drug's dosage, the drug's bioavailability, times the elimination, to the power of negative absorption and time. Moving on from that, we have our equation for elimination. When calculating elimination, we have our elimination constant, the concentration of what's left in the drug, and the drug distribution volume in the body. Now, moving on to the formulation of the differential equation. The end goal, as seen on the left side of the equation, is to find the concentration over time of the drug. To do this, we will be using the smaller equations I mentioned in the previous slides. As you can see, we have our elimination and our absorption. The elimination will be subtracted from the absorption. This will calculate the measure of a drug left in the body at the different points in time, once divided again by absorption. Now, keeping the equation in mind, we will move on to new variables. First, we have the amount of drug being absorbed over time. Then we have the amount of drug being eliminated over time. During the absorption phase, the body is absorbing the drug faster than it is being eliminated, which in turn causes the concentration to increase in the body. During the elimination phase, the body is eliminating the drug faster than it is being absorbed, leading it to its excretion. Lastly, from the equation earlier, we have an example of a solution we would typically see as a result. You can imagine this taking place during the steps of LADME. Once the drug is consumed and begins entering the bloodstream, there's a steep rise in concentration as the drug absorption is greater than the drug elimination. This then levels out a little at the point of max drug concentration, before leading to a steep fall where the drug absorption is less than the drug elimination, which in turn leads to a more gradual fall as it reaches excretion. In pharmacokinetics, math is applied to find the concentration of drug over time, to help provide doctors with a proper prescription to issue. This involves the use of a differential equation, which takes the combination of variables to find the drug's elimination and absorption, to ultimately find the drug's concentration over time, typically showing the result of a steep rise and a steep to gradual fall as the drug goes through the 5 steps of LADME. I hope this small and brief presentation of some of the math behind pharmacokinetics will help provide some insight into the thought of what a proper dosage of certain drugs look like. Thank you.